Imagine a bell, silent and cold for billions of years, suddenly struck by an unseen hammer. Instead of a quick, fading chime, it resonates, it vibrates for nearly an entire hour. Now, imagine that bell is our moon. What if everything you thought you knew about our silent, unchanging celestial neighbor was wrong? What if the moon, the same comforting orb that graces our night sky, hides a secret so profound, so alien, that it fundamentally redefines our understanding of cosmic geology? That's exactly what happened over 50 years ago when humans intentionally hit the moon. And what we learned was far more unsettling than anyone could have predicted. Back in 1969, the world watched, captivated, as Apollo 12 made history, placing astronauts Pete Conrad and Alan Bean on the lunar surface. But their mission wasn't just about planting flags and collecting rocks. It was a bold, unprecedented experiment. After Conrad and Bean rendezvoused with the command module in orbit, the mission controllers back on Earth did something extraordinary. They intentionally crashed the discarded lunar module ascent stage, the part of the spacecraft that had just brought the astronauts back up from the surface, right into the moon. It was a planned impact designed to kick off a brand new field of science: lunar seismology. The astronauts had left behind seismometers, instruments designed to detect ground tremors, and everyone expected a dull thud, a quick tremor that would fade away almost instantly. What they got instead was a cosmic reverberation that lasted for almost an hour, slowly, eerily tapering off. The moon, it seemed, wasn't just a rock. It rang like a bell. This wasn't a one-off anomaly. Later, during the Apollo 13 mission, when a critical oxygen tank explosion forced the crew to abort their lunar landing, their massive Saturn V rocket's SIVB third stage was also deliberately crashed into the moon. This impact was far more powerful than the lunar module, equivalent to roughly 11 tons of TNT. And again, the moon rang. This time, the tremors lasted for over 3 hours, traveling thousands of miles across its surface. It was as if the moon was a vast, hollow gong, struck hard enough to sing. Scientists were bewildered. Earth, our home planet, with all its geological activity and diverse terrains, absorbs impact energy almost immediately. A meteorite hitting Earth might cause a local earthquake, but the vibrations quickly dissipate. The moon, however, was acting completely differently, holding on to that energy, letting it echo and reverberate in a way that defied all initial predictions. This isn't just a cool fact, it's a profound difference that speaks to the very heart of the moon's terrifying nature. To understand why the moon rings like a bell, we first need to understand what makes it so fundamentally different from Earth, geologically speaking. Our home planet is a dynamic, living world. It's covered in oceans, crisscrossed by tectonic plates that constantly shift and grind, and its interior is a swirling, molten inferno. All of these features, the water, the soft sedimentary layers, the fractured crust, the convection currents deep within, act like a giant dampening system. Think of it like this. If you hit a bell made of gelatin or covered in thick blankets, it wouldn't ring much at all. The energy of the impact would be absorbed, muffled, and spread out almost instantly. Earth is, in a geological sense, a very squishy planet. The moon, on the other hand, is the exact opposite. It's an ancient, desolate world, bone dry, with no atmosphere, no oceans, and no discernible tectonic plate activity. Its surface is scarred by billions of years of impacts, but beneath that dusty regolith, its crust is something else entirely. Its crust is incredibly rigid, brittle, and largely homogeneous. There are no oceans to absorb shock waves, no thick layers of sediment to dampen vibrations, and very little internal friction within its deep structure. When the Apollo 12 lunar module slammed into its surface, that impact energy had nowhere to go. It couldn't dissipate into water, couldn't get lost in moving tectonic plates, and couldn't easily be absorbed by soft, malleable rock. Instead, it propagated. It traveled through that dense, unweathered material, bouncing around inside the moon's interior almost unimpeded, like sound waves echoing in a massive, empty cathedral. Think of our bell analogy again. Earth is like a bell made of lead, buried in sand. Hit it, and you get a dull thud. The moon, though, is like a perfectly cast, enormous bronze bell, hanging freely in a vacuum. Hit that, and it will resonate, singing its deep, low note for a very long time indeed. The moon's low internal friction is a critical component here. On Earth, as seismic waves travel, they encounter various materials and discontinuities which convert some of that wave energy into heat. This absorption quickly reduces the intensity of the vibrations. On the moon, that energy conversion is minimal, allowing the waves to travel vast distances and persist for extraordinary lengths of time. This isn't just a scientific curiosity, it's a terrifying insight into the very nature of a body that was once considered geologically dead. So, we've established why the moon rings. But why is this terrifying? On a fundamental level, it reveals a geological. Consider the implications of this lack of seismic dampening. If an impact on Earth produces a quick, localized tremor that fades in seconds, an equivalent impact on the moon generates a sudden, violent shock wave that can persist for literally hours. For future lunar bases, this isn't just a nuisance, it's an existential threat. Imagine a moderate meteorite strike, far smaller than the one that created the Tycho crater, slamming into the lunar surface. On Earth, this might create a localized crater and perhaps a small, short-lived earthquake. On the moon, that same impact could generate intense ground shaking across hundreds or even thousands of miles that continues for what feels like an eternity. Picture a human habitat on the moon, a sealed dome or underground tunnel meticulously designed to withstand the vacuum, radiation, and extreme temperatures. Now imagine that habitat being subjected to over an hour of continuous, severe vibration. We're not talking about a gentle sway. We're talking about the kind of shaking that could fracture structural supports, rupture critical air seals, snap delicate equipment, and disorient or injure anyone inside. There would be no gradual warning, no slow build-up to the peak, just a sudden, violent jolt followed by an hour of relentless, bone-rattling oscillation. The very ground beneath your feet, which you rely on for stability and protection, would become an enemy, a constantly vibrating, potentially crumbling surface. For colonists, this isn't just an inconvenience, it's a catastrophic potential. Every moderate impact, every piece of space rock slamming into the moon becomes a potential hour-long assault on their fragile shelters. How do you design structures to withstand that? How do you sleep soundly, knowing that at any moment, the very ground could begin to sing a deadly tune for 60 minutes or more? The moon's resonant nature implies a level of geological instability that makes long-term human habitation profoundly challenging, turning what seems like solid ground into a drumhead, waiting to be struck. The moon isn't just trying to kill us with radiation and vacuum, it's also trying to shake us apart. And the terrifying implications don't stop there. The moon lacks a thick atmosphere, which means it's constantly bombarded by micrometeoroids, tiny dust-sized particles to pebble-sized rocks that burn up harmlessly in Earth's atmosphere. Every single one of these impacts, no matter how small, becomes a mini seismic event on the moon. While these wouldn't necessarily cause hour-long tremors from small impacts, it suggests a constant, low-level chatter, a continuous series of tiny reverberations, making the moon's interior a strangely active, unpredictable place. It's like living inside a snare drum that's always being lightly tapped, only occasionally being hit by a mallet. This constant ringing also suggests something unsettling about the moon's structural integrity. The way the energy propagates and persists hints at deep fractures and possibly even vast internal voids. The moon isn't a solid, uniform sphere. It's likely a complex, perhaps even hollowed out, structure that's more unstable than we initially thought. Imagine building a house on Swiss cheese. This structural unpredictability makes any long-term construction or mining operations on the moon incredibly risky. You might drill into what you think is solid rock, only to find a cavernous, unstable void. So, the moon we thought we knew, the quiet, inert rock hanging in the sky, is actually a dry, rigid, and shockingly resonant place. It's a cosmic bell, poised to vibrate for hours with every significant impact. This isn't just about the absence of air or water. It's about the very physical instability of its geology. Even a comparatively small impact can unleash long-lasting, ground-shaking consequences that would be catastrophic for any permanent human settlement. The moon isn't just challenging because it lacks the elements for life. It's actively hostile in its fundamental physics. It's a haunting reminder that space isn't just empty. It's filled with worlds that operate on rules utterly alien and sometimes terrifying to our own. If you found this cosmic truth as unsettling as we did, make sure to check out our next video right here.